Hello, let's continue our journey through climate. So we've talked about what generally controls your climate. Your latitude specifically is the biggest single factor. Your elevation can determine how your climate acts. The higher up you go in elevation, it makes you cooler, just like increasing latitude will make you cooler. Um, we've talked about the effect of water on your climate. Obviously, water adds humidity to the air, but water also moderates your temperatures. It doesn't let you get too hot in the summer, it doesn't let you get too cold in the winter if you're near the water. Those are the biggies we've talked about thus far. You also have the windward and leeward side of the mountain. The windward side, the side the air goes up first. It's going to be cooler and more humid on that side because rising air expands and it cools. And on the leeward side, the air gets compressed again under the weight of more air above it in the atmosphere that warms it up and it doesn't have moisture in it. So it's often drier on the leeward side of the mountain. So now we're going to continue talking about air in the atmosphere in terms of atmospheric circulation. Now, weather is very short term. Climate is your long term average. And obviously, what we just mentioned controls your climate. But there's also bigger patterns that circle not just, Watertown, New York or Dexter, New York, but these are global patterns. And that's what we're going to go into here with atmospheric circulation. There's certain patterns that control the conditions globally and keep it the way it is. So there's a large scale permanent circulation pattern in the Earth's atmosphere that happens due to convection. Now, we've talked about convection before. Convection is the circulation of things that can flow due to density differences. So, when air gets warmer, it gets less dense, and the warm air rises, and cooler air takes its place. That's the fundamental thing that goes on. Air near the surface warms up, it rises, cool air replaces it. Now, that motion creates wind at the surface. It also creates circulation in the atmosphere that can move warm air to new places and move cold air to new places and mix the energy around on the planet. So, it's caused by the fact, and we've talked about this numerous times, that the Earth is a sphere. And as a sphere, only one place on the planet can have direct sunlight at any given point in time. So there's an uneven heating of the Earth's surface. Some places get very direct sunlight, other places it hits at an angle, and you end up with different amounts of heat and temperatures as a result of that. So uneven heating of the Earth's surface causes this. You end up, especially with the equator, is clearly a warm spot. Direct solar rays most of the time. So you'll end up with warm air rising off the equator almost every day because it's warm there pretty much every day. And eventually that air cools off as it gets high enough and it'll want to sink back down again. So you end up with these circulations. Here's the first one from the equator rising up and then sinking back at 30 north or 30 south. But there's other ones. So that's what we're going to talk further about here. So the warmest air on the planet hangs out near the equator. That warm air rises. And the coldest air, of course, is at the poles because they go 6 months at a time without sunlight at all. And even when the sun is up, it's not very high in the sky. So if the Earth just stayed still in space and didn't rotate or do anything else, you would expect to have a huge continuous convection cell with warm air rising at the equator, like in the picture here, the warm red arrows, and then cold air sinking at the poles, and it would just flow down toward the equator where it would warm up, and then it would come back up toward the poles, and you'd have this giant convection cell. But the thing is, the Earth does spin. And as the cold air comes back toward the equator, it does warm up too. So it starts to rise long before it gets to the equator. So it's not quite that simple, but that's the concept. Warm air rises, cold air sinks, and it moves between those places. So the circulation pattern between the equator and the poles is messed with because of the Earth's rotation. The Coriolis effect, remember that curve to the right in the northern hemisphere or curve to the left in the southern hemisphere, due to it, causes winds to curve. And so we don't end up with straight line winds. We end up with swirling patterns, curving patterns. We discussed that low pressure systems go counterclockwise in the northern hemisphere, high pressure goes clockwise in the northern hemisphere. So counterclockwise northern, clockwise. Yeah, okay. Don't think I've said that wrong. So, since we rotate once every 24 hours, since there is the Coriolis effect, we don't end up with one convection cell. We end up with 3 on either side of the equator. Now, the picture's a little different here, but this is very similar to what's in your reference tables and you'll have access to on tests. So we need to get used to this simplified but complicated picture. It's simplified in the fact that it's not 3-dimensional. It's complicated because there's like 100 million arrows on here. So the green represents the Earth's surface as a whole. You have the equator going across the middle, poles at the top and bottom. The red arrows or blue arrows just represent the normal way wind blows at those latitudes. So on the surface of the Earth, you would expect this direction of wind most of the time. And above the green here, all the way around the outside, all these loopy arrows, that's what's happening in the atmosphere. These are our convection cells. And they go around the whole globe, but we don't really show it in this flat picture. So at the equator, you have warm air rising. By the time it gets up to about 30 north or 30 south, it gets cold enough where it sinks again, and you end up with a convection cell there. From 30 north to about 60 north, you have a circulation pattern going on there, another convection cell. And then way up at the poles, you have the cold air sinking, flowing back to the south, where it eventually rises up at about 30 north, or 60 north, pardon me. So you have these convection cells, and it's same in the southern hemisphere also. We just tend to focus on the northern hemisphere because that's where we live. So at the boundaries between these cells where they're running into each other, you have 2 options. At the surface, you can have winds coming together, i.e. converging, or they can be going apart from each other. If you're at a convergence zone, so the equator and 60 degrees north and south of the equator, you have winds at the surface coming together and warm air rising up. And that's what happens in both of these spots. Now, when warm air rises, it cools off. When it cools off, it makes clouds, assuming there's enough moisture in the air, and there always is, and can lead to more precipitation. So these areas tend to have clouds and precipitation because air is usually rising there at convergence zones. So rising warm air causes a flow inward. When you take warm air off the surface, that creates low pressure. So the winds come rushing in to fill that low pressure. And low pressure is counterclockwise inward circulation. Low pressure systems are weather systems that we've talked about before. So these areas have a low pressure on them most of the time, therefore they have warm, humid climates, just because of the fact of where they are. So if you look at a satellite view of the Earth or look at a map, and you plot out where rainforests are, where the world's great forests are, they're going to be in these zones because forests need precipitation. They need a climate that allows for the trees to grow. Now, the opposite of that, instead of coming together, now we're going to go apart at the surface. That's a divergent zone. Divergent zones happen at 30 north and 30 south, so 30 degrees latitude either side of the equator, and also at the poles. Here, cold air is sinking. When it gets to the ground, you have high pressure there. The wind's going to go out away from where it was sinking because more cold air is coming down behind it, and then it spreads out and heads on opposite directions. Divergent means go apart. So at these zones, the winds at the surface are spreading away from that area. You have sinking cool air that creates high pressure, and you end up with the circulation that is appropriate for high pressure. So it's gonna, in the northern hemisphere, be clockwise and outward away from that zone. Southern hemisphere rotation is opposite, but again, we focus northern hemisphere. So we have high pressure zone there. Now high pressure is nice weather, but it tends to be dry. So if you have high pressure, you're probably not gonna have clouds and rain much. So these areas are cooler than you might have expected otherwise. but that's not their big claim to fame. The poles are obviously cold. They're very arid. So these latitudes are super dry because of the sinking air there. So most of the world's great deserts are found right near 30 latitude, either 30 north or 30 south. And the poles are pretty dry too, but we don't think of them as, they're obviously not sandy deserts, but they don't get that much precipitation. It just doesn't melt from year to year. All right, so here's kind of the 3D prettier picture again. We have our convergence zone at the equator. So clouds are there because you have rising warm air. That air sinks back down at 30 north. Both of these cells do. And as a result, it's dry at 30 north and at 30 south. So that starts to get low in the picture. At 60 north, you have more rising air. It's not as warm there by any stretch, but you still have rising air. And so that leads to more humidity and more precipitation and wetter climate. Now, this is the picture from your reference tables. This is on page 14 at the bottom in your reference tables. And so this is the one we really need to get familiar with. No pretty colors, no three-dimensional wrapping around showing you the convection cells. You just have to realize that the circle here represents the Earth, and all the arrows in it are surface winds in the direction they normally go from. And above that circle, there's your atmosphere, the lower part of the atmosphere especially. And you have the convection cells in there. So there's often on the regions a lot of questions or some questions about this, and they're very simple. You just have to find the right latitude, so like the equator, let's say, and it might ask, is the air rising above it, or is it a convergence zone? So as long as you know convergence means come together, you can look and say, oh, there's the equator, winds are coming together, and they're rising off the surface, and that leads to a wet climate. So it tells you a lot on the diagram. You just have to be able to interpret it. So convergence zones happen at 0 and 60 latitude, and divergence zones happen at 30 and 90. One way to remember divergence zones, die is dry. You die if you get too dry. Divergence zones are dry zones because the air is sinking there. Die is dry. So here's a color picture composite view of the Earth's surface, all stretched out to be a rectangle. And what you notice, if we put the latitudes on here, so our convergence zones are at 0 and they're at 60. So 60 south, there's nothing there. So there's no land, it's all the ocean. But if you look at 60 north, that goes through northern Canada and Russia and Scandinavia up here, it's pretty green. I mean, long winters, so they have lots of snow in the winter. This would be more of a summertimey picture. But it's pretty green because the world's great coniferous forests are there. The taiga, if you remember doing biomes in the past, this is where you have taiga, a lot of coniferous trees. And at the equator, it's very green here as well through Indonesia and Central Africa and northern part of South America. That's where you have the world's great rainforests because, again, it's warm there, the tropical rainforests, and it's a convergence zone. If you look at the divergence zones, the poles are the poles. They're dry, but they stay snowy. Here you go. High pressure zone, the cooler arid divergence zone here. Again, it's 30 degrees, so it's not really cool, but it is very arid. You have the northern Mexico, the desert southwest in the U.S., the Sahara Desert across Saudi Arabia and such, Gobi Desert. You can see it's pretty sandy color there. It gets a little messed up over here in the north of India because you have the Himalayan mountains there. So the windward side of the mountain stays green and it's dry behind it. But these aren't solid lines that the winds can't cross realistically. They move a little bit, but you can definitely see it's drier there. And in the southern hemisphere, there's not as much land, but again, fairly dry in the southern part of South America, especially the Atacama Desert. Down here by the southern part of Africa, you can see some tan showing up. The central portion of Australia is a god-awful dry desert. It's like one of the driest places on the planet. So again, it's just based on where you are in those convergence or divergence zones. So we have these winds that develop on the surface of the Earth, the surface prevailing winds, sometimes called planetary wind belts. And This is the direction the winds normally flow due to where you are on the planet in the convergence and divergence zones. You don't have to memorize these. These are on, like I said, on your reference tables on page 14. We live at about 45-ish north, 44 north. All of the continental United States really falls in there. And as we've discussed before, weather usually comes from the west and goes to the east. The reason for that, where we are, is the prevailing westerly winds. We typically have a westerly flow. If you go a little further north of us, easterly flow is kind of a thing. When we talked about hurricanes briefly, hurricanes come across from the coast of Africa and end up in the Gulf of Mexico or the Caribbean over here. They move that direction because at around their latitude in the tropics, the winds actually go from the east to the west. They go the opposite way. Once the hurricanes got up a little further north, the westerly winds grab them and kick them back off into the Atlantic. So these winds happen on the surface of the earth because of where you are in relation to those convergence and divergence zones. Now, like the trade winds are named that because traders figured this out long before there were meteorologists. They knew that they had to get closer to the equator if they wanted to sail from Africa or Europe and get to the New World. And when they wanted to go back, they would sail further north and catch the winds to get pushed back over in the opposite direction. So sailors sort of figured this out because that was how they could move. So some of these have names associated with that fact. Similar diagram, not too much different there. I just discuss it when you're here. All right, so between convergence and divergence zones, a series of planetary wind belts develop, just mentioned that, and that determines the flow and movement of weather systems across the surface of the Earth. So these prevailing winds, or what they're called, push weather systems around. And that influences your climate because if weather keeps getting pushed from the same direction at the same time of year, it's going to influence what happens over the course of the long term. So here's a map of today's jet stream. So over the continental United States right now, up in the stratosphere, just above the troposphere into the stratosphere, so we're talking 6-7 miles up, you have this rapidly moving band of air. And this guides storm systems around, pushes them, holds them back, or lets them go. And typically in the wintertime, the jet stream dips down about the middle of the country. So it lets cold air come down out of Canada, warm air come up from the south. And so we end up being cold, and the southeastern US ends up with a much milder winter. This year, it's for the most part stayed north. So we've had a pretty mild year, except the last couple of weeks. And Texas, of course, had their cold stretch last week where they had all sorts of trauma. That's because the jet stream let the cold air come back down again. How this jet stream moves and changes guides the weather patterns and it controls what's going to go on. Now, there's certain normal summertime paths and wintertime paths of the jet stream. It's predictable or somewhat predictable, but it doesn't always do the exact same thing. So typically you have a polar jet stream, which again, this time of year sort of cuts the country in half, lets the cold air down and keeps the warm air away from New York. You have the subtropical jet stream, and the same in the southern hemisphere. How that jet stream moves controls where the warm cold line is. If the jet stream moves up, it lets warm air come up over the continental United States. If the jet stream stays low, it allows the cold air to come down. Now, normally with the seasons, we do get a shift here. Summertime, the jet stream hangs out central Canada, lets the warm air come up. Wintertime, it's more across the central US. That's typically what happens to control our climate. Similar diagram, just showing it from the side-on view, because this does happen above the surface of the Earth. But again, your polar jet stream hanging out over the US, really, in our particular case, and it varies with the seasons. So I've mentioned this term several times already in the video. Prevailing winds just means it's the wind direction that you normally have in an area. So winds always blow from high pressure to low pressure. That's non-negotiable. They're always going to do that. So these prevailing winds develop between divergent zones and convergent zones. Divergent zones have high pressure, convergent zones have low pressure, and so the winds blow from divergence to convergence, guaranteed. And they do curve due to the Coriolis effect. So in North America, as I mentioned, we usually have prevailing westerly winds. The flow starts from the south, kind of curves, and goes across the United States, across our continent. So here we go. South of us, so Florida is at about 30 north. South of us, the winds are from the northeast to the southwest. We tend to have winds going from this divergence zone to the convergence zone north of our country, and they curve to the right a little bit to give us prevailing westerly or southwesterly winds. So you can see across our continent, same deal, all at that latitude. Now, mountain ranges can get in the way, big land masses or big ocean areas can adjust the winds a bit. These are just general normal patterns. The positions of these wind belts do change with the seasons because of the jet stream. In the summertime, they move northward. In the wintertime, they move southward, just like the path of the sun changes during those seasons as well. Now, one place where you have almost certainly heard about this is global studies, where they talk about monsoon season. The monsoons happen because of this. So in the wintertime, you have this situation where you have high pressure up here over Mongolia and lower pressure down here over the Indian Ocean, lower latitude, warmer conditions. And so the winds tend to go from high pressure to low pressure. So the winds come across the Himalayan mountain range here, across India, out into the ocean. That means the winds that go across India, with its almost 2 billion people, are very, very dry. Going over the windward side of the mountain and down the leeward dries them out. And so you get warm, dry winds. Not real great for rain or growing crops. So that's the dry season. Now, when the monsoons come, that's more moving on into the summer months. The high pressure that was here over northern China and Mongolia, that shifts a little further away. And we have a low pressure that develops over the Middle East, kind of over here off to the west of India, Pakistan. And so now the winds are allowed to come up to fill in where this lower pressure is. They come onshore and bring life-giving moisture from the Indian Ocean here as they go across the continent. They dump rain on the southerly side of the Himalayas. And that's what the monsoon season is all about. When that high pressure moves north, it allows the winds to come off the ocean. Some years the monsoons fail. That means the jet stream doesn't shift and things don't line up properly. And that's when they have serious issues with not enough water to raise their crops. So monsoons are caused by this, which you've learned about in global studies. Now, it's also the reason we have hurricane season, or at least part of it. In the winter months, the jet stream's lower, and it does not allow, one of the things that does not allow hurricanes to form is because the jet stream is so low that if we did have a low pressure system come off from Africa, it would be closer to the equator where it doesn't have enough spin and it just doesn't work. So as a result, during these seasons, the trade winds move the tropical storms and hurricanes towards the southeastern United States from the tropical Atlantic. This is in this, like from May till October, we're going to have possibility of hurricanes because the jet stream moves north, the warm air moves north, and it allows these storm systems to come across the Atlantic towards us. So winter months just doesn't happen because of the shift in the jet stream. But October to August, that's what I said. From about May, honestly, to October, It said August, but due to global warming, things have kind of picked up, and so we have hurricanes earlier in the year. Once the ocean water is over about 85, it's on, and it can be hurricane season. You do have them in the Atlantic as well. It says December to June, so they can get them a little sooner in the, I said Atlantic, Pacific. Um, the Pacific is a bigger ocean, more heat available over here, so similar seasons. Um, in the southern hemisphere, the hurricane season is switched, so when we're not getting hurricanes, they typically are with not much overlap. That's the reason we have hurricane season. All right, and we'll come back and talk about this in lab, I think, but ocean currents are caused by winds going across the surface of the ocean. And this is another map in our reference tables. Ocean currents can also influence your climate. It's really a simple one, so I'll just give you the quick highlight here before I shut up. If you live in an area near a warm ocean current, it keeps you warmer. If you live in an area near a colder ocean current, it keeps you cooler. So California over here has the California current next to it. I think this is on page like 4 or 5 in your reference tables. I forget on this one. But it keeps California cooler than it would be otherwise because any winds coming onshore are going to have to go across the cool ocean water. Now, on the other side of the continent, the Gulf Stream over here, that's a warm ocean current. The symbols are down below. The Gulf Stream going off the shore of North America and taking warm water into the North Atlantic keeps areas that are influenced by it warmer than they would be otherwise because the ocean and water holds a lot of energy and it can move it around very effectively. So we'll go into more about the specifics, but generally speaking, ocean currents are pretty straightforward. Warm ocean current keeps you warm, cold keeps you cold. End of story. Close the door, turn off the lights. Pretty straightforward. All right, so I think that'll about do us for today. We've got our convergence and divergence zones. You need to remember those, what forms them, what they mean, which way the winds are going, and that's on page 14 in your reference tables. So thanks for watching. Have a good